next session is going to be about galaxy systems, so pairs, groups, and clusters. And the first speaker is Riccardo Scarpa, talking about galaxy pairs.
Well, first of all, thank you to the organizer for making all this possible, and thank you for allowing me to speak. This is a project that I carried out with two Italian collaborators, Riccardo Scarpa and Riccardo Scarpa. This started a few years ago when Natale and Chamarot, two French investigators, they started building a large sample of pair of isolated galaxies in order to study their orbital velocity. They started from the Hyperlera catalog, which included at the time 4 million entries. The selection criteria they followed are shown here. The most important is that galaxy absolute beam magnitude had to be brighter than minus 18.5. This means that there is a cut in absence of dark matter. There is a cut in mass when you cut in luminosity. This is extremely important for the final result. So they selected big galaxies. Then the projected separation between the two pairs on the sky had to be smaller than 1 megaparsec. The radial velocity for the galaxy to enter the separator to be within from 3,000 to 16,000 kilometers per second to make the peculiar motion negligible. And the radial velocity difference between the two galaxies had to be smaller than 500 kilometers per second. And this defined a pair if the radial velocity was close enough. No multiples. Each member had to be the closest to the other one, and then an isolation criteria was created, taking into account the distance of the nearest galaxy to the pair. Okay, so the ratio of the nearest galaxy to the pair divided by the pair separation. Okay, and they ended up with a pretty large catalog with 13,000 pairs with a moderate isolation parameter. With an higher isolation parameter, they had 7,500 pairs. And you can see here the distribution of intervelocity. So the difference of velocity between the two galaxies is absolutely monotonically decreasing with no indication of anything special. So Natale and Chamarot were able then to develop a technique to project the observed intervelocity distribution. And here I show you an example, because you certainly are not familiar with this, where I show you a fake set of 12,000 velocities, okay, distributed as a flat background plus a Gaussian. Then this one is randomly projected on the radial direction. You get this distribution, and this distribution is the input for the projection technique, and the technique is actually able to retrieve that there is a preferential velocity on this set of 12,000 galaxies. This was easy. This is another example. In this case, there are two preferential velocities in a background. And again, the projected distribution is just monotonically decreasing and nothing special. But again, the input value could be retrieved. And this gives you and give to us good confidence that we could actually retrieve some peculiar velocity if there was one. Okay, so this is the initial result that Natale and Chamarot presented. So again, this is the observed intervelocity distribution. As you can see, nothing special. And then they ended up with this they projected distribution. Now, this would be the three-dimensional velocity the three-dimensional orbital velocity of galaxy pair. And this clearly indicated that there is a preferential value over almost flat background. Okay, Natale and Chamorro didn't present an answer or an explanation for this preferential velocity, and of course there was no mention whatsoever of MOND. On the other hand, as soon as we saw this, we immediately thought that there had to be a preferential velocity, because in MOND the separation of the galaxy disappeared, and the velocity only depends on the mass of the pair. Okay, but before actually doing the calculation with MOND, we wanted to confirm Natale's result, and we reapplied the exactly the same technique on a newer version of the hyperledger catalog that had increased by the time Natale used it of 20%. So now we had 5 million entries, and we ended up with a set of galaxy pair of 16,000 pairs compared to the 13,000. And again, you can see here the distribution of the intervelocity, which again is monotonically decreasing with no indication of a preferential velocity. This is actually the projected separation, where you can see the closest pair are preferred, obviously, because it is asked not to have other galaxies nearby. And the result we obtained fully confirmed the initial suggestion by Natale and Chamorro. Here you can see the two distributions that are virtually the same, and the two results. This is the Natale results, and then down here our own result with more data. Please note that the presence also of this secondary accumulation of values, which represent the galaxies, the pairs that would have a differential velocity larger than the limit imposed to the sample. So it's not actually something special for the velocity. It's simply because the sample is scattered at 500, but one pair that has an intervelocity of 1,000 can project within 0 and 500. Okay, and so all that accumulation of values represent the galaxies that are certainly not bound. And the amount of contamination is expected to be high, and actually it is extremely important to attempt at least to quantify how many false pairs there are. Remember that we had no idea of a pair is actually a physical pair or not, and there is no way to know it, at least at present. So, for instance, we did a back of the envelope calculation, just assuming that the 170,000 galaxies from which this sample is derived were uniformly distributed on the sky, because there are so many, and to define a pair, we put a limit of 1 megaparsec in projected separation. So there are so many galaxies that basically every galaxy has another galaxy nearby. And indeed, you expect, simply for pure statistics, you expect about 7,000 pairs, which had to be false pairs, compared to the 16,000 pairs that we found. So basically, almost half of the pairs had to be false pairs there. Okay, and another way to quantify the contamination is to maintain the position of the sky, on the sky of the galaxies, and randomly exchange the radial velocities. Okay, you maintain the same set of radial velocities, but you randomly rearrange them among the galaxies, and again you end up with a significant amount of contamination, and indeed we found about 4,000 false pairs. So all these indicate that indeed there is a large contamination. So our claim is that all the pairs outside the peak are actually unbound chance alignment. This is the basic hypothesis to explain the peak. And here we see the mass distribution. As I said at the beginning, it is extremely important that there was a cut in luminosity. So this is a plot of the mass as a function of distance. As you can see, the mass of the pair does not depend on the separation. This is a bit unexpected, because you would say that more massive pair would survive the larger separation. Okay, but the important thing is that the full sample covers only just 1 dex, approximately 1 order of magnitude in mass. And because in MOND the separation is not relevant, we end up with an easy prediction. So basically, in Newtonian dynamics, the intervelocity should decrease with separation and no preferential intervelocity should be observed. On the other hand, in MOND, because the mass is is limited to 1 dex, you expect to have a preferential velocity. And so our proposal is that the peak is actually a direct consequence of MOND. It is I have to point out that the interaction between galaxies always happen on deep MOND regime, and this allows us to apply the formulation for the deep MOND regime, in which there is an exact solution for the two-body force. I have to thank Micron for helping us on this. And so we use these formulas to calculate for each pair, given the mass of the pair, calculate the expected velocity. And we ended up with this distribution here, okay, down here, where you can see the distribution of calculated velocities according to MOND, and the Gaussian is the Gaussian that describes the fit, which has been resampled to increase accuracy. As you can see, there is a perfect match between observation and the MOND prediction. Okay, with all the caveats about contamination, etc., it seems that this new piece of information, because no one had information about the galaxy velocity, is well described by MOND. Okay, of course there are alternative explanations. Pawlowski will talk later on this Congress about the presence of the same peak in numerical simulation. I only comment here that in the simulation, the galaxy halos are built in a way to impose Tulip feature. And so basically they impose the galaxy to behave as MOND. And so it is not a surprise that they will, if they find a peak. Okay. So going further, the catalog that we use, the XLED, basically includes all nearby galaxies or known nearby galaxies. This means that to build a completely independent set of galaxy pairs, we require to move at higher random velocity, which means that the cosmology will become important, at least to define the projected separation. And so the question is, but which cosmology are we going to use? Of course, in the context, in the framework of MOND, you don't want to stick on a cosmology that depends on the existence of dark matter. So I will propose here something new, but new in a radical way. Okay. So what I'm proposing is to get rid of expansion. So for a moment, forget whatever you know about cosmology and start thinking in the old fashion. Okay, so we have the Hubble relation, which is interpreted as due to expansion. In this case, there is no expansion. So the redshift has to be the result of something else. Okay, then there is the cosmic microwave background interpreted as the remnant of the Big Bang. Again, in this case, there is no necessity for the Big Bang. There are many other results supporting the ΛCDM scenario, but not a single one is 100% conclusive. So please be patient and just concentrate on the data. Okay, if you want to introduce a cosmology, you need to introduce a way to measure distance. Of course, we already know that in the local universe, the Hubble law works pretty well in giving us the distance of galaxies. So we take the Hubble law and we just apply it to all redshifts. It is linear to all redshifts, no matter how large is the redshift. And we use the H0 value, which is measured 70 kilometers per second. We have no free parameter whatsoever, nothing to play with. Once you have defined a distance, you can define a luminosity distance, because you need a relation between flux and luminosity, which is the traditional Euclidean one you learn in high school. But you have to introduce, and this is the magic, this is the term that actually do the magic. So, because we know a photon from a distant galaxy is carrying less energy, okay, when it reaches us. And so you have to decrease the luminosity by this factor in order to get the flux. And with this, you can define the luminosity distance if you want to retain this concept of luminosity distance, but there is only one distance in this framework. And of course, the angular size distance is given by the Hubble law. So the size of distant object have to decrease as the inverse of redshift. Okay. Apparently, this was rejected decades ago, but it's not the case. Okay. The first unexpected result of this basic assumption is that the luminosity distance we all are used to use is actually numerically almost identical to the luminosity distance I already defined. You can see here on the upper plot, you can see the comparison of the two distances, which are virtually identical up to redshift 5. There is in the two never differ more than 10%. Okay, and they actually start diverging only for redshift larger than 10. This is quite unexpected. Okay, and this is the famous plot that everybody apparently is able to explain nowadays. This is the Hubble diagram for type 1 supernova. Remember, this is the Nobel Prize winning plot. And you can see here, even you can see only one line. There are two lines there. The ΛCDM description of the data and the Euclidean relation. Okay, that I just show you. You can find more information on the paper shown there. Okay, the big differences between the two cosmologies arise when you start talking about the size of distant sources. In an expanding universe, the angular size distance does something very weird, because distant objects should appear extremely large on the sky. And this is actually the behavior of the angular size distance in ΛCDM, where you have a minimum at around redshift 1, and then the apparent size of a standard rod will start increasing instead of decreasing. On the other hand, in the Euclidean scenario, the relation is this one, and it has to decrease. Okay, the two are completely different. This has important consequences for instance, for the Tolman test for surface brightness dimming. You know that the surface brightness of distant galaxies should decrease as 1 plus e to the cube. Okay, but this is not the case. Okay, if it was true in an image like the Hubble deep field, nothing should be visible because all galaxies should be way below the background. Indeed, here is an implementation of the Tolman test up to redshift 5, where you have a set of reference samples, and for every sample in the local universe, RS basically 0, then you have the corresponding sample, and galaxies here have the same luminosity. Well, I use the time for the question.
There won't be time for questions.
Okay, then, well, I can skip this one. Well, this is the situation. You can see the claim now with James Webb data is that galaxies are extremely small. But let's have a look at this data. As you can see, this is the most distant I could find in the literature is at redshift 16, when the universe, according to ΛCDM, was 250 mega years old. If you go to study this galaxy and you take the radar profile, you see that this is exactly described by an exponential disk. With no indication whatsoever that this galaxy is merging or is doing anything strange. It's just a fully formed, relaxed galaxy, which has an effective radius of 0.1 arcseconds, so it's very small. And the corresponding size is 0.3 kiloparsec in ΛCDM. Otherwise, in the Euclidean scenario, it is 30 kiloparsec, the effective radius. And here is the important plot. This one is, well, in my opinion, an amazing plot extending to 16 in redshift. You see this set of values are the sizes of the distant galaxy discovered by the James Webb. Galaxies that have 10 to the 10 solar masses are probed in the UV rest frame. Okay, this is extremely important because the UV is only sensitive to the young stellar population and are not affected by the accumulation of red stars that you would have at redshift 0. So this sample, the local sample at redshift 0, then you have the intermediate samples at 2, 3, 4, and 5 in redshift, and then you have this new bunch of values. The samples are almost matched in luminosity because the new ones they are a bit brighter, but nevertheless you see the size goes as expected in a static Euclidean non-expanding universe. Okay, this data severely question everything, and so let me have the
minus 5 meters.
Okay, let me have my last slide is just a suggestion to use MOND and the typical characteristic of the rotation curves to discriminate between the two cosmologies. This is an example, the best one I could find. Perhaps Federico has better example now. This is the rotation curve of a galaxy, okay? And the authors, they published this work, they decided at this point the curve became flat. Okay, they arbitrarily put at 0.22 arcsecond, the position where the flattening started, and the velocity at that point is 280 kilometers per second. So if you invert, you end up with an effect, a radius where the acceleration of the R0 corresponds to 1.5 kiloparsec. You see, this is the scale in the ΛCDM scenario, and these are up here, is the scale in the Euclidean scenario. So, if you compute the acceleration at that particular radius, you'd end up in ΛCDM with an acceleration which is way above, in this case, about 10 times A0, A0. On the other hand, if you use the Euclidean value, you end up with a value which is fully consistent with A0. Okay? Also, you can place the galaxy, if interpreted in the static scenario, you can place a galaxy in the Tully-Fisher relation. On the other hand, you cannot place the galaxy in the Tully-Fisher relation. And even more problematic for the ΛCDM is the fact that the mass of a distant object is, again, the product of the velocity squared times its size. But the size is computed to be extremely small, which means that you end up with a dynamical mass which is smaller, I repeat, a dynamical mass which is smaller than the luminous mass, which is a physical impossibility. This is a total no-go for the ΛCDM. And this has already been observed. We didn't have to wait for the James Webb. And for instance, there is this paper where they present a bunch of cases where this is already, this had already measured. And I stop here because otherwise they
There is time for a couple of short questions. So Marcel has one.
Okay. Hi, Marcel Pronowski, AIT. Thank you. Thanks for the nice talk. Okay, so I shot. I don't want to shot here, actually, but. So yeah, and just a comment on you put up our work, and I just wanted to mention that the intent originally was to check an ЛCDM and find it doesn't work, and then kind of really have a big success for MOND. Unfortunately, it seems to work in ЛCDM that you find a peak in the intervelocity. I will not talk about that tomorrow, so just a little correction before anybody expects that. I talk about more interesting things, I know. But my question is, why don't you really expect that? If you, in say, Newtonian sense, if you have a distribution of galaxy mass, distribution of distances, and you just calculate the circular velocity, like we did for the simulation, you find some distribution in the intervelocity, and for the observed systems, it seems to be that there's a peak expected if you account for the dark matter mass.
Well, I'm not sure I understood your question, but it's, you're talking about the preferential velocity observed in galaxy pairs.
Yes.
Okay, well, that is a result that in Newtonian dynamics is difficult to understand because, first of all, the dependence of mass on the mass of the pair is stronger in Newtonian dynamics. It goes with the root square of the mass, while in MOND it goes with the fourth root of the mass. Okay, so the mass basically disappears in MOND, but it remains relevant in Newtonian. And then there is the fact that the velocity had to decrease with separation, while in MOND it doesn't decrease. So basically, once you have a bunch of galaxies with approximately the same mass, you end up with all moving at the same orbital velocity, and you get a preferential velocity. In Newtonian dynamics, no, because the pairs have different separations, so you have a spread in the orbital velocity.
I agree that you have a spread, but you still get a peak. That's what I mean. I mean, if you look at the simulations we investigated, you look at the pairs there, you calculate the circular velocity in Newtonian, you still get a peak. If you assume the dark matter mass just happens to be there. But anyway, we can discuss that offline.
All right. We're already over time, so we invite the next speaker, and in the meanwhile, let's thank Riccardo.